All right, Pre-Cal 12, let's get after it. Here we go, video 3. We're now going to look at geometric series. So similar to a arithmetic sequence and series, remember that a sequence was just the list of numbers, and this would be arithmetic, right? Common difference. The series was when we added it all together. So we get the same thing with geometric. We're going to add our geometric series together. So Sn, right, that's the sum of n terms, is equal to my first term, right, my a value, times 1 minus the ratio to the power of n all over 1 minus the ratio. Now you could also use this equation, and that's when you know the last term. You don't need the number of terms in the equation because you know the last term, so you're good to go. So we can use either one of those, and we're just going to do a few examples. This is a rather short video because it's just seeing the equation in action. So always consider what you have. You can see here, I have my first and I have my last, so I'm going to use this equation. I don't need to worry about the rest. Now the thing is I still don't know how many terms I have, but it doesn't really matter. We can still say the sum of the n terms present is the first term minus the ratio times the last term all over 1 minus the ratio. Now, what's our ratio? Well, 2 times 3, 6 times 3, 18 times 3. Okay, so we get A is 2, L is 1,458, and R is 3. And then again, remember, this just becomes color by numbers. So the sum of n terms is 2 minus 3 times 1458 all over 1 minus 3, which is negative 4,372 over negative 2. So we get a sum total of 2,186. So there's nothing overly complicated here. It all comes down to the information that you have, and we can move from there. So let's look at another one. Now, in this case, you can see I've changed the equation we're going to use, and I've changed it because we don't know the last term, right? But we know that we're going to have 7 terms of this geometric series. Now, if you really wanted to identify our common ratio, so times 2 times 2, you could just keep writing out that list and write down all 7 terms. But why would you do that when you don't have to? Because what do we know? We know that we want the sum of 7 terms. So n is 7, a is 3, and in this case R is 2. So we have enough information to plug into our equation. So the sum of 7 terms is equal to 3 times 1 minus 2 to the power of 7 all over 1 minus 2. So in this case it's 3 times 1, 2 to the power 7, 2, 4, 8, 16, 32, 64, 128. So 1 minus 128 over negative 1, which gives us 3 times negative 127 over negative 1, which gives us negative 381 over negative 1, which then gives us the sum 381. So again, nothing overly mind-blowing here, just more practice with the equation. Now the one thing we get into here again is the summation notation. So the capital letter epsilon. And we have, in this case, k equals 1 on the bottom and n is 10 on the top. Now remember that your n value is n minus k plus 1. Because just think, n minus k gives you the difference between 10 and 1, but we also need to include the number 1. So that's why we add the 1 at the end. So how many terms do we have here? We have 10 minus 1 is 9, plus 1, we have 10 terms. Right, so n is 10. Now, what they want, though, is they want us to write this sequence, or this geometric series, in summation notation. So in our example there, my n value is not 10. How many terms do I have, right? I have 1, 2, 3, 4, 5. So that means my n value at the top of my epsilon is a 5. My k value is 1. But now how do we write this? Well, let's look. What's my common ratio? My r is equal to 3. But then we got to kind of see, is there a pattern to this? Well, because if I just put 3 to the power of k, that means my pattern would go 3, and then 3 squared, 9, and then 3 cubed, 27. But that's not my pattern here. So you kind of got to reconcile the difference to that pattern, right? So what is happening from, when you have 3 to become 6, when you have 9 to become 18, when you have 27 to become 54, there's a pattern there as well. Every value is multiplied by 2. So that needs to be included in your summation notation. So we can rewrite it as the sum of n, k equals 1. Well, in this case, my n is 5, and I have 2 times 3 to the power of k. Now, quick note, if you are doing a geometric series, the variable, the k value, is going to be in the exponent. Remember when we were doing a arithmetic, the variable was in multiplying with the base, because a common difference is repeated addition, which is multiplication. But a common ratio or common multiplication, repeated multiplication, is an exponent. So there's the subtle difference there. So that's all we got for this one. Look through the notes if you want some extra examples, but it is, again, quite straightforward. The next thing we're going to look at, though, is an infinite geometric series, one that goes on forever. And there's subtle pieces to it, some interesting aspects of it. So stay tuned for that video. It'll be coming up next. Thanks so much, and I'll see you next time.